Okay, Calculus 1, we are going to begin to talk a little bit about average velocity, trying to develop the idea ultimately of what a derivative of a function. Okay, so to begin with, we're going to talk about what average velocity is. Average velocity turns out to be the slope of a line where you have some sort of a position function. S of t generally is going to represent the position at a time t, ends up being the slope of the line. I'm going to pull up this applet. This is kind of a nice applet that shows you how this works with a basic function. So I kind of like this, and this helps you establish the idea of what instantaneous velocity is also. So this is a curve. This blue line represents s equals 16t to the second, represents a position. The average velocity is going to just be the slope of this secant line. So for instance, if you look at these points, you have a point 264 and a point 4256 on this curve. So you would go through and you would basically find the slope of the line. So you would do the rise over the run and calculate that out if you wanted to. Now I could go through and change this velocity. Okay, here's 3.2 seconds. Okay, that slope, average velocity is changing. So I want you to notice on this as we go this way, it's getting less steep. So at 2.3 seconds, the average velocity is a little smaller. And then since the line's going to get steeper, you'll kind of notice as I go like this, the average velocity is getting steeper, so the average velocity is increasing. Eventually, we'll kind of look at the idea of an instantaneous velocity would end up being, once we get 2 points that are really, really close to each other, infinitesimally close to each other, then we get what's called the instantaneous velocity. Okay, so back on this illustration, okay, what we usually say is we're going to say the average velocity on this, and a lot of times we write this like this, it's a change in y values. So we might say it's a slope, so it's a change in y values over the change in time. So we write it like that. So in general, we would write this, in this particular case, we would say s of t2 minus s of t1. That would give you the change in these y values. So, you're kind of looking at that rise right there, which is going to be defined by this. And then you would have the difference between the x values, in this case would be t values, and then that would give the run. So the run would be the distance between these two things, which is t2 minus t1. So you would end up getting this formula for an average velocity. So it's doing nothing more than finding a slope, okay? Okay, so in this diagram down at the bottom here, we can think of the average velocity as the total distance traveled over the total time taken. Okay, again, this is just a difference between the position at two different times. Total time taken is just going to be the difference between those two times like that. Now the slope formula that you're familiar with is if you had 2 points, x1, y1, and a second point, x2, y2, then the slope is y2 minus y1 over x2 minus x1. That's what you're familiar with, so think of the average velocity as just a slope of a secant line. And a secant line goes through 2 points, and then a little bit later on we'll talk about what a tangent line is, and a tangent line is just touching 1 point on the function in a small neighborhood around that point, okay? All right, so moving on to this next thing, we'll crunch out a few things on here. Well, first of all, we're going to sketch a graph on this one. I'm going to use my graphing calculator mostly on this, but let's go ahead and do one by hand because I don't want people to forget about the ability to do this by hand. So let's go ahead and let's just sketch out a graph on this. And just do this one by hand to start with here. So let's go ahead and make an axis kind of like this. Now I need to flip that thing up the other way. Okay, so that should give us a nice picture on this. So we're going to label this as the x-axis, and then this is going to be the y-axis. And we're going to go from 2 to 4. This is supposed to say we're interested on the interval 2 to 4. So let's go ahead and break up our x-axis, go up to 4, like this. Just doing this by hand. Now what we're going to do is we're going to find function values on this. So what I'm going to do actually is just make a little table of values on this then. So let's go ahead and let's make a table of values. Just kind of get everything crunched out. Then we'll go to our graphing calculator and do that. Okay. So I'm just going to be interested in these x values on here. I'm interested in 0, 1, 2, 3, and 4. And we're going to crunch those things out then. Okay, so we're just going to do 0 squared plus 0. We're going to evaluate this function x squared plus x and just kind of do that one at a time. And get that crunched out. And do the arithmetic, then we'll have a pretty good graph, and then we're going to look at finding the average velocity like this. So we're just going through and evaluating this one by one. So of course that's going to be 0, so you're going to have a point 0, 0. This is going to be 1 plus 1 or 2. This one's going to be 4 plus 2, so that's going to be 6. This one's going to be 9 plus 3, so that's going to be 12. And then this one's going to be 16 plus 4, so that one's going to be 20. So let's go ahead and scale this kind of like this. Let's go, that's 10, let's say that's 20. Maybe scaling that by 5s, like that. And then we'll go through and we'll just plot our points. So we have a point 0, 0. We have a point 1, 2. We have a point 2, 6. 3, 12. And 420. So this is a quadratic equation, a quadratic function. So it's going to do something kind of like that. Okay. So what we're going to do is we're going to find the average velocity on the interval 2 to 4. So what we're interested in is we're interested in this point and this point. I'm going to go ahead and label those. This point right here is the point 2, 6. And then this point right here is the point 420. So what we end up having is we end up having a secant line that we can find the slope on then, okay? So what I'm going to do here is go ahead and just sketch out kind of roughly a secant line on here. Okay, kind of get this lined up a little bit better here. Okay, so we're going to end up finding the slope of that secant line, okay? All right, so that's what we need to do. When we find the average velocity now, what we're going to do for this average velocity is we're going to end up just taking y2 minus y1 over x2 minus x1. Okay, so we're looking at the 2 points, 2, 6, and we're looking at the point 420. So finding the slope of the secant line, we're just going to subtract the two y values. Okay, you really pick the order that you want to do that in too. So that's going to be equal to 20 minus 6. I'm going to do it that way. Then I need to do the x values in exactly the same order. So I'm going to subtract those that way. Okay, so that's going to give 4 minus 2. So we're finding the change in y over the change in x. So that's going to be 14 over 2. So that's going to be 7. Okay, and you would end up having on that some distance over a time. So that would be what the average velocity on that particular problem is, like that. Okay, so that's how you would do that. Now I want to just kind of remind you of the power of a graphing calculator, because you want to be able to do this, you know, by hand, and then also be able to use your calculator. So if I put in the function that we're graphing, which is x squared plus x, and then if I want to go from 0 to 4, I'm going to set this up the same way that I did here. I'm going to go 0 to 4, scale of 1. Y, I'm going to go 0 to 20. We can scale that by 5 if we want to. And then we can construct a graph. So that's your quadratic like that then. Now what I'm going to do is I'm going to move that over there for a second and just show you a couple of things that you can do on this then. So that would be the graph that would come out of your graphing calculator. which is kind of a nice, accurate graph. And then really what you're doing is you're doing basically the same thing on this. You're locating the 2 points. We had the point 2,4, or 2,6 rather, is what that point was. Okay, so I'm going to label that as 2,6. Label this as 420. Okay, and again, what you were doing is you were finding the slope of that secant line that goes through those 2 points like that. So that's the idea of what you're doing, is you're finding the slope of that secant line. Okay? All right, so that works out to be 7. Okay, now let's go to a next example here. We'll use our graphing calculator to help us a little bit with this one also. Okay, so this one I'm going to go ahead and just use the calculator. This one is going to have an asymptote on it, and we're interested on this one on the interval 4 to 7. Okay, so I'll pull up my calculator, and we're going to go ahead and put this one in. So we're going to put 3 divided by, and then we got to have parentheses x minus 2. Okay, and since we're going from 4 to 7, what I'm going to do on this is I'm just going to make it go, say, 0 to 7, like that, by a scale of 1. If you want to figure out how to scale your y-axis, since we're going from 0 to 7, if you go second graph to get the table to come out, then you can just kind of look at values from 0 to 7. So you're going to notice you have a plate, you're undefined at 2, and when you go up to 7, you got pretty small values. The biggest value of y I see there is 3. So I'm going to go back, when I make my window, I'm going to go 0 to 3, scale of 1. And then that should be a pretty good picture of our graph, like that. Okay, now I'm going to move this over here. And then we'll just kind of draw on this for the purposes of this graph. I'm just going to put this over here. If you were doing that by hand, you would have to just do a table of values like I did the last problem. Okay, so here's what we got. We're going out to all the way to 7, and we're interested from 4 to 7, so that's 654. We're interested in this point, and we're also interested in that point right there. And then the y-axis, I have that set up so it's going 1, 2, 3 like that. So what we're going to do then on this is I'm just going to draw a secant line again. And again, the idea is this secant line is going to go directly through these 2 points. That thing won't get on the grid very good. So the idea, you kind of see the idea is you've got that secant line going through those 2 points like that. So you can tell you have a negative slope. So what we need to do is we need to figure out what these points are. That has an x value of 4, and then this has an x value of 7. Okay, so if we go through and do this, what we would have is f of 4 is 3 over 4 minus 2. Okay, so that's going to be 3 over 2, or 1.5. I'm going to go ahead and just use fractions, so that's 4 over 3 over 2. Then I'm going to do f of 7, which is 3 over 7 minus 2, so that's going to be 3/5. Okay, so when we find our average velocity, we need to use those points. Now you can use decimals on that or fractions. It doesn't really matter too much on this. Okay, so the average velocity is really just the change in y over the change in x. And in this particular problem, the y values are these. So I'm going to pick the order I subtract it. So I'm just going to go 3/5 minus 3/2 all over the change in x, which is going to be 7 minus 4. Okay, so I'm going to work this out. I need to get a common denominator on the top, which is 10. So I can multiply this by 2 over 2, and I can multiply this by 5 over 5 to get a common denominator. So that's going to be 6/10 minus 15/10, and then that's going to be all over 3. So that looks like that is going to be negative 9/10 all over 3. And see what that is that's just a division problem. So you're doing negative 9/10 dividing by 3 over 1, so that is going to be negative 9/10 times 1/3. Okay, you can reduce that fraction if you want to right now. So that goes to 3 over 1. So we would end up having negative 3/10. And in terms of decimals, that's going to be negative 0.3. So we can write our answer either as negative 3/10 or negative 0.3. Either one's okay. Now you can use decimals on this also. So if you change this to decimals, that's like 1.5. That's 0.6. So you could also do this problem like this. The slope is going to be 0.6 minus 1.5 over 7 minus 4. So that's going to be negative 0.9 over 3. And if you divide that on a calculator, you should get negative 0.3 anyway. So you can do that either way. Okay, so that is a velocity that's negative. Average velocity is negative on that interval. Something to do with grid. That's got something to do with some sort of a grid thing there, I think. Take that off is what you want to do. You don't want to snap that to the grid. So I was just going to see if, real quick, if I did that, is that snapping to a grid? It doesn't look like it's even snapping to a grid, and I don't want it to do that anymore. If I do that, I just want it to kind of go like that. And yeah, that's clearly the way you do that. So with the next thing on the next page, as I continue through this, we'll have you try a couple of problems. I'm going to go ahead and pause this and just let you try to do the next two problems yourself. Okay, so let's go ahead on this one and let's do a graph ourselves. We'll use the graphing calculator on this also, but just for something a little bit different, let's go ahead and make a table of values on this one. And I'll kind of do this at the side here. And just get our 2 points and maybe a few extras to get a nice plot on this. So what we're going to be doing is we're going to be finding the average velocity on the interval 2 to 8. So we're going to have x and we're going to have y equals the square root of 2x. So I'm going to just pick some values like 0. I'm going to pick 2. And I'm also going to pick 8. And that's probably good enough to get a pretty decent graph on this then. So what we're going to be doing is square root of 2 times 0. We're going to use the function. Then we're going to do square root of 2 times 2. Then we're going to do square root of 2 times 8. So this is going to be square root of 0, so that's 0. This is square root of 4, so that's 2. This is square root of 16, so that's going to be 4. So now we can go ahead and sketch our graph. So let me get a good coordinate system here put together. And then we'll go ahead and find our average velocity. So what I'm going to do on this is just go out to 8. So we got 1, 2, 3, 4, 5, 6, 7, 8. We need to go up to 4 on the y-axis. So I'm going to go 1, 2, 3, 4 to get all the points put there. So I've got a point 0, 0. I've got a point 2, 2. And I'm going to label that. Then finally I got a point 8, 4, which I'll label like that also. Then I'll sketch in the curve of that square root function like that. So that is the graph of y equals square root of 2x. Okay. All right, now what I'm going to do is I'm going to go ahead and I'm going to sketch my tangent line on this. So I want to, or not tangent line, the secant line. So I just need to be sure I connect these 2 points that I'm going through kind of carefully like that. So we're finding the slope of that secant line. Okay, so what we're going to do is the average velocity is just going to be, again, change in y over change in x, or that's y2 minus y1 over x2 minus x1. Okay, so if you go through and look at our y values are going to be 4 and 2. So we're going to subtract those two. And then the change in x, we'll do that in the same order. We're going to subtract 8 and 2. So we're going to do 8 minus 2. Okay, so we should have a positive slope, so that's 2 over 6, which would reduce down to 1/3. So that would be the average velocity on that particular example. Okay, so that's doing that without the graphing calculator. You can use a graphing calculator when the graphs are a little bit more challenging to do, but you want to be able to do it both ways. Okay, right? Next problem. We're going to be looking at a sine. One thing I wanted to just kind of mention on this is what happens on this problem too is what you're really doing is if you're kind of doing like a rise over a run, like you would have learned in an algebra class. So that is delta y, and that right there is delta x. Okay, so you're going up 2 over 6, and that reduces down to a ratio of 1/3. Okay, the next one, we'll go ahead and do this one without a calculator, just for the purpose of review primarily. Okay, so on this one, we're going to be sketching out the graph of y equals sine of 2t, and we're going to be graphing this on the interval from 0 to pi over 4. A couple of things on this I want to remind you of. The amplitude on this is 1. The amplitude is the number that's in front of the sine. The period of a sine wave, we have a formula that is 2 pi over absolute value of b, and b is basically that coefficient of the variable t. So that means the period is going to be 2 pi over 2, or that's equal to pi. Okay. Then we're going to increment our x-axis. Anytime you want to figure out a good way to increment the x-axis, what you want to do is you want to just take the period and you want to divide that by 4. So you're going to get the period pi divided by 4. So that will tell you the way that you need to increment the x-axis. So again, what we're going to do on this one is we're going to go ahead and sketch a graph, this time without the calculator again. And we're just going to look at from 0 to pi over 4 is basically what we're interested in. Okay? So what I'm going to do on this is I'm going to go ahead and take the graph out a little bit further, mainly for the purpose of review. So I'm going to go like pi over 4, count out to 2 pi over 4, 3 pi over 4, and to 4 pi over 4. So I'm going to go ahead and take my graph all the way out to pi. Now you would obviously want to reduce these fractions, so that was going to be pi over 2. So I'm going to go ahead and take that one to pi over 2. And then this one will reduce the 4's cross out, so that's going to reduce down to pi, like that. So what's going to happen on this one then is we're going to go up to amplitude of 1. I'm going to go ahead and go down to a minimum of -1 and just use this to review. So the way you would do this is we know that the sine of 0 radians is 0. So that's going to start there. Then it's going to hit its high point. Then back to the x-axis. Then its minimum. And back like that. So that's going to be what we're looking at, is that sine wave from 0 to pi like that. Now in this particular problem, we're interested in the average velocity on these 2 points. So what I'm going to focus on is this point 0, 0, and this point here, which is pi over 4, 1. Okay, then we're going to just sketch out a secant line, and we're going to find the slope of that secant line to find this average velocity. So I'm going to take a line that's going through those 2 points. Okay, like that. So we're going to be finding the slope of that secant line. Okay, so the average velocity, again, is going to be the change in y over the change of x, which will be y2 minus y1 over x2 minus x1. Okay, so when we do the values here, we're going to subtract the y values, 1 minus 0. Okay, then I'm going to subtract the x values, pi over 4 minus 0. Okay, so that's going to give 1 over pi over 4. And that really is dividing two fractions. So you would end up having 1 times 4 over pi. So that means the average velocity would be 4 over pi. Okay, and you could get a decimal answer on that also. So if I got my calculator out, sometimes it's good to get decimal answers on this. So if I just go 4 divided by pi and maybe round that off, that would be approximately a slope of about 1.27. Okay, so I'll say it's about 1.27. Okay. Okay, so that's how that would go. Now I want to show you on the graphing calculator, if you're dealing with a trig graph using technology, first thing you want to make sure is that you're in radian mode and that you're in function mode. Now if you go y equals, we're just going to put in sine of 2t, so we got to put in sine of 2x. Okay, I'm going to do the same thing that I have here. I'm going to go ahead and graph from 0 to pi, just so you can see the one period. You can scale that by pi over 4. That increment is pi over 4, so that's why I'm going to scale that by pi over 4, so you can see the key values. And then the y minimum, I'm going to go just like I did on this. I'm going to go negative 1 to 1 because I know the amplitude of this is 1. And I can graph that, and then you'll get the same graph that I've got here then. Okay, so that's how you would punch that in on a graphing calculator to get an accurate graph using technology. But we're still doing the same thing on this. This problem, what we were doing was we're looking at the point pi over 4, 1, and the point 0, 0. And then what we were doing was we were looking at the secant line, finding the slope of the secant line that goes through those 2 points, like that. Okay, so that's a technological approach to getting that graph down. Again, you want to be able to do that both ways. Okay. Okay, so the next thing I'm going to do is we're going to look at technology to kind of help us with getting the idea of making a conjecture about instantaneous velocity on this then. So I'm going to pull my calculator out because we're definitely going to need this to do this conjecturing on here. So I'm going to clear everything off of my calculator, and we're going to go ahead and we're just going to put in this function. So we have a quadratic here that we're going to be plotting out. So we're going to go ahead and put that in the graphing calculator. So that's going to be x to the second, and then minus 5. Now that's going to be a quadratic that has been shifted down 5 units. So what you would end up having on this, I'm going to just make my window. Since I'm interested at t equals 0, I'm only going to do a small area around this. So I'm going to do like maybe negative 2 to 2 for my x-axis. Actually, let's make it more like negative 3 to 3 because I want to see the x-intercepts good. And then scale that by 1. Now the y minimum, see, we know we have a minimum of negative 5 on that quadratic. So let's just go down to, say, maybe negative 10. And let's go up to maybe 10 on this is a good graph. Okay, so I'm going to do that. And then what I'm going to do on this is I'm just going to go ahead and just get this moved over here so we can kind of refer to that. And then this would be, of course, a very easy graph to just do by hand, just getting enough points. So I want to kind of go through and show you what we got set up on here now. So I was making the x go from negative 3 to 3, and I was making y go negative 10 to 10 like that. Now what we're interested in is we're interested in the instantaneous velocity. And the instantaneous velocity is going to end up being a tangent line. So we're really interested in a tangent line on this. So if I was just going to go sketch a tangent line, the idea on a tangent line is if you took just a small neighborhood around that, you want to find a line that's only going to go through, touch that small part of the curve in one point. So if you just kind of think about this a little bit, I mean, it looks to me like probably more than likely that's going to have a slope of 0. You can kind of tell by looking at that, but that's what the tangent line is. That's what we're interested in, is finding the slope of that tangent line. And we're going to do this with numeric methods using our calculator to kind of assist us with this. So what we're going to do is we're going to close in like this. We're going to take points that we're going to get closer and closer to t equals 0 from both sides. And I'm going to use this trace command to fill this in. So I'm going to type trace, and I'm going to start by filling in all these values on the calculator. So I'm going to do negative 0.1, then I'm going to record that. So that's going to record as about negative 4.99, like that. So we're kind of interested in what's happening on that function then, okay? Up. Okay, and just kind of show you what this means in the context of this problem. So the idea is, if you look at this diagram right here, the idea is as these 2 points get closer and closer to each other, this average velocity gets closer to the instantaneous velocity. So the closer I get on that, the closer that's going to hit to just a tangent line. So you kind of think, right now I've got 2 points, that's a secant line. Eventually they close in so close that for all practical purposes you can consider that secant line approaching a tangent line. That's kind of the idea that you want to get established, okay? All right, so I'm going to have you go ahead and work out the next one. I'd like you to do a graph. You can use technology, fill out the table, and then make a conjecture about the instantaneous velocity. Okay, so moving on with this one, I'm going to get my calculator out, and what I would have liked you to have done is just graph this quadratic so that you get a pretty accurate graph. So I'm going to have x squared plus 8x minus 2, like that. And we're interested at t equals 2. So we need to just, on our window, we don't have to graph the whole thing. We're just interested in how this graph is behaving around 2, a little less than 2 and a little bit right of 2. So I'm going to just go ahead and I think I'm going to do it like this on this problem. I'm going to just graph from 0 to 4 by a scale of 1. And we can use the y and just see what this looks like. All I got to do is just get a pretty good idea. So we're going from right around 2. So let me expand on my y just a little bit. Let's go negative 10 maybe to 50 by a scale of 10 and see if we get a pretty good picture on this now. Okay, so that looks pretty good. I'm going to move this over here, and just so we'll have kind of the graph to refer to on here. Then we're going to fill out our table and kind of make a conjecture. So the way that I have this set up is I have t is going to 4. So this is your t-axis, and then this is your s of t axis, and I was making that go all the way up to 50. So we're going by tens, kind of like that. Okay, so what we're interested in is what's going on in this graph at 2. If we're going to find the instantaneous velocity, what we're interested in essentially is what is the slope of this tangent line. At this stage, all we can do is close in on a secant line. So clearly you can tell you have a positive slope on this one. So you're going to have a positive instantaneous velocity. So what I'm going to do using my calculator is I'm just going to trace out at these values. So again, what I'm going to do is I'm going to start less than 2 and greater than 2. Then I'm going to close in towards t equals 2. I'm not going to hit t equals 2, but I'm just going to close in on it to get the idea of the limit established. Okay, so let's start by tracing at 1.9. And that's going to record. We'll record that as 16.81. Let's close in at 1.9. So now I'm going to trace at 1.99, getting a little closer to 2 from the left. And now that's going to be 17.8801. Now let's close in a little closer using 3 decimals, 1.999. Record that. That gives a little greater accuracy, 17.98001. So it looks like we're heading towards that looks like you're heading towards right about 18. Okay. Now let's start over here and let's trace at 2.1. So if I trace 2.1, that's going to give over here 19.21. Then we want to close in a little closer to 2.01. Okay, that will give a little closer. That's going to be 18.1201. And then let's go a little closer still, 2.001. And then record that as right around 18.012001. Okay, so remember what we're doing is we're estimating what the average velocity is. So the average velocity, we could take 2 points on here that are close. We can take these 2 things right here and those 2 x values like that. So if I go through and work on this with the calculator, you're going to end up having, again, change in s of t. We're going to do the change of the function values over the change in time this time. So the average velocity, I'm going to use 18.012001 minus 17.988001. And then the change in time is going to be 2.001 minus 1.99. And we're going to crunch this out to make a conjecture on this then. Okay, so let's see, that numerator 18.012001 minus 17.988001. So I'm going to record that as about 0.024. And then when we do subtract the t's, 2.001 minus 1.999 with 3 decimals is going to give about 0.002. Now we'll divide the 2, which you can do in your head. That's 0.024, and then divide that by 0.002. Should give us a slope of about 12. Okay, so that would be the answer, is it looks like that average velocity, that instantaneous velocity is going to be right at 12. Okay, now eventually we're going to learn calculus methods so that we can quickly crunch this out once we learn about the derivative. Okay, so that just means the instantaneous velocity is going to be about 12, and usually that's going to be in like meters per second, feet per minute, something like that. So that's what you should have came up with on that problem. Okay. Okay, moving on to the next thing I want to look at. Okay, so on this next one, we're going to look at this function. You have a quadratic, and we're going to estimate the slope of the curve. Now, if it's asking for a slope of a curve at a point, that's talking about a tangent line. That's not a secant line. You're only given 1 point. You're going to use a table of values to estimate this. So this is going to be one that we're going to, again, use some technology on. So let's go ahead and graph this. So I'm going to go to my y equals button and put in x to the second plus 5x. We're interested in x equals 4. So what I'm going to do on my table is I want to kind of close in around x equals 4. So I'm going to look at, maybe starting at 3.9, then going 3.99, 3.999. I'm just getting closer to 4 from the left. Then I'm going to close in from the right. So I'm going to do something like 4.1, 4.01, and 4.001, kind of using similar increments when I do that. Okay, so as far as a window on this, since I'm interested in 4, I'm going to go maybe 2 to 6, scale of 1. I'm going to graph in a similar window. I'm going to make my window go from 0 to, I'm going to say like 80 maybe. Let's try that. 0 to 80, 2 to 6. And that's a pretty good graph. And then I'm going to put this on here. And then we're going to trace and do the table of values. I just kind of got the graph to refer to. So what we did on the graph on this is really 2, 3, 4, 5, 6. This is not the y-axis, so this is kind of going out, a little bit further like that. Then I think I made this go up to 80, so like that, by tens. So this would be 70, 60, 50, that's 40. We got that. So what we're interested in is we're interested at t equals 4, and we're interested in the slope, again, of the tangent line, not the secant line, but we're going to use technological methods to estimate what the slope of that tangent line is. So that's what we're ultimately going to do, is find that slope. Okay, so what we end up doing with this now is we're going to do some tracing. So let's start at tracing at 3.9 and recording. So that's about 34.71. Go in a little closer, 3.99. Just gets closer to 4. So that gets 35.8701. Close in a little closer, 3.999. Okay, I'm going to trace at that point. And then that's going to give about 35.987001. Now let's start over at 4.1. So let's trace at 4.1 and get what that is. Okay, so at 4.1, that's about 37.31. Let's trace a little closer at 4.01. Record that as 36.1301. And then finally, let's trace a little closer still, 4.001, and record that as 36.013001. So one thing you can tell is this y value, you can tell, is getting close to 36. Okay, so what we're going to do now is we're going to figure out the instantaneous velocity. So we're doing the instantaneous velocity on this now. So that's going to be the change in y over the change in x. So we're going to use these two y values. So we're going to use 36.013001 minus 35.98701. And then we're going to use the x values that associate with those and do that. So we're going to have 4.001 minus 3.999. Use the calculator to crunch this out and to approximate then. Okay, so on a clear screen, let's do the numerator, 36.013001, and subtract 35.98701 and record that. So that's going to be about 0.026. Okay, let's do the bottom. We got 4.001 minus 3.999. And that's going to be about 0.002. Now we can divide the two. You can do this in your head. So 26 divided by 2 is 13. Okay, and that should give us the instantaneous velocity, or the slope of the curve. So that's 13, so that would be the answer to that problem. Okay, so that's how that works out then. And again, we're going to learn a little bit simpler way to use calculus methods to do this a little bit later in the class. Okay, so let's see. Let's do one additional one that I'll let you all go ahead and try. So I'm going to go ahead and pause and then put you all to work on this. Okay, so I'm going to go ahead and get everything erased on my calculator, and this is a cubic function, so I'm going to put in x to the third and minus 5x, and get a graph. We're interested in x equals 1, so all I'm going to do on this is maybe go something like 0 to 2 or something. So let's go 0 to 2 by a scale of 1. If you look at the table of values between 0 and 2, looks like you got some negative values there on that. So I'm going to do that. I think I'm going to go ahead and just go negative 2 to 2 like this. This is just my decision. There's no right or wrong way to do that. I'm going to go negative 2 to 2. And then for the y minimum, I'm going to do something like negative 5 to 5. And that may very well get all the data put in. So I'm going to try that window. There's a graph. That'll be good enough for what we're trying to do. Okay, and let me get this graph put up here at the side. Okay, so I got this set up like this. I just decided to go negative 2 to 2 and 5 to negative 5 like that. So what we're interested in this point is we're interested in the slope of the curve at x equals 1. So what you're going to find on this then is you've got this point right here at x equals 1. So you're interested in that point. And then the slope of the tangent line, just for visual purposes on this, you'll notice that if we do the slope of that tangent line, it'll do something kind of like that. Now, it's only touching in kind of a small neighborhood. So clearly the number one thing is you have some sort of a negative slope. All right, so setting this up, we're interested at 1, so we're going to close in on it. So from this side, let's just say that we are at 0.9, and then close in a little closer by a decimal going that direction. So we're going to close in that way. And then closing in from this way, let's take 1.1, and then 1.01, and 1.001. That way we're closing in at the same kind of increments. And what we're going to do on this is we're going to do a table, just trace this out. So I'm going to start at tracing at 0.9. Okay, and that's going to give, in my table, 3.771. I'm going to trace at 0.99, getting a little closer to 1. So that's going to give 3.979701. Then we're going to trace in at 0.99 with 2 decimals. I like that. Actually, with 3 decimals is what I'm deciding to do on this, I think. So I need to put 3 decimals in here. Okay, so that's going to get us to about 3. I want to make sure I'm doing the right thing on that. I hope I've been tracing right on that. Let me try that again. I may have been kind of overlooking what I'm doing here, because what I'm wanting to do is close in from both sides like this. So let's do that again. If I trace at 0.9, I think I've been forgetting about my negative. So that's going to be negative 3.771. Now trace at 0.99. That's going to be negative 3.979701. And then trace at 0.999. And that's going to go to negative 3.997997. Okay, then let's go the opposite direction. So let's get a little bit to the right of 1. Let's do 1.1, which is negative 4.169. Let's go to 1.01. Okay, and that will be negative 4.019, I think, 699. And then finally, let's trace in at 1.001. And that's going to leave us at about negative 4.001997. So you can kind of tell you're approaching negative 4 as you go through that then. Okay? All right, so when we do the instantaneous velocity, or if we do the slope of the curve, that again is going to be change in y over change in x. So we're going to use these two y values, the ones that are close together, for the greatest accuracy. So that's negative 4.001997. Subtract negative 3.997997. And then the denominator, we're going to do these two, 1.01 and that. So we're going to do 1.001 minus 0.99. Like that, just using the calculator to get this approximated down. So I'm going to clear everything off. And let's see. We're going to have negative 4.001997. Now we got a plus here. Okay, because if you notice in here we got a minus minus, so we're going to add 3.997997 and record that as negative 0.004, and then the denominator you're going to do 1.001 minus 0.999, and that will give you this. And then this one, again, you can do this one pretty much in your head. So if you divide those two things, you're going to get negative 2. Okay, 0.004 divided by 0.002 will leave you with that answer. Okay, so that's it. You can tell we have a negative slope on that problem. So that will end up the discussion for this section. This is mostly trying to get you attuned to the idea of a derivative being the slope of a tangent line that we'll get to pretty soon. Okay, hope that helps you understand everything in this section.